Welcome to today's Explainer. I was digging through some fascinating engineering documentation recently, and honestly, it took me on a pretty incredible journey under the hood of Python. We're going to track the complete life cycle of data inside your code today. We'll start with the simple variables we define, all the way down to understanding the complex object identities that Python is quietly managing completely behind the scenes. Whether you're whipping up a quick automation script or architecting a massive application, mastering how Python handles data is absolutely the key to writing clean, efficient, and bug-free code. So let's jump right in.
Before we even look at a single line of code, let's stop and ask a really fundamental question. How does Python actually store and understand data? When you type a number or a word into your script, how does the interpreter know exactly what you mean, where to put it, and what you're actually allowed to do with it? Well, that is exactly what we're going to unpack.
Here's our roadmap for the journey today. We'll quickly cover the basics of variables, Python's fundamental data types, mutable versus immutable types, data collections, and wrap up with checking types in Python. Okay, let's dive into this.
Section 1. The basics of variables. Let's set the rules of the game.
Every time you assign a value in Python, you're basically carving out a little piece of memory. But as Oregon State University's engineering docs point out, Python is remarkably strict about how you name those variables. Break these rules and your code is going to crash instantly. You absolutely must start your variable names with a letter or an underscore. After that, you can throw in letters, numbers, and underscores, but strictly no spaces. It's also vital to remember that Python is perfectly case-sensitive, so a lowercase n and an uppercase n create entirely different variables. You also got to steer clear of Python keywords like for or if, and definitely avoid using built-in function names, otherwise you'll just overwrite them and cause massive headaches down the line. A quick pro tip for you. The preferred convention in the Python community is to use all lowercase letters separated by underscores.
Let's actually put those rules to the test with some examples. A name like var space 3 fails simply because of the space character. For x_a fails because it starts with a number. That just confuses the parser immediately. Data file name fails because of the spaces again, and %pop hash is completely invalid because of the special characters. Seeing the allowed names compared directly to the forbidden ones really solidifies those rules. It's a simple mental checklist, right? But getting this right from the very beginning saves you from those endless, incredibly frustrating syntax errors when you're deep in a coding session.
Moving right along to Section 2, Python's fundamental data types, from integers to dynamic typing.
This brings us to a super powerful and honestly sometimes confusing feature, dynamic typing. In older languages, like C or Java, you have to explicitly declare what type of data a variable is going to hold before you ever even use it. You literally have to tell the computer beforehand, hey, this variable will only ever hold an integer. Python doesn't do that at all. If you type a = 2, Python automatically assigns it as an integer at runtime. If you type b = 4.5, it instantly knows it's a float. The Python interpreter does all the heavy lifting for you, figuring out the type based purely on the value you provide the exact moment the code runs. Pretty neat, right?
Now, speaking of floats, here is a highly practical tip when you're dealing with very large or very small floating point numbers. Typing out long strings of zeros is a massive trap. Seriously, don't do it. It's incredibly difficult to read, and miscounting just one single zero can silently ruin an entire calculation without throwing a syntax error. It's a literal debugging nightmare. Instead, always use scientific notation, represented by an E or E. It's significantly cleaner, way safer, and it immediately communicates the exact scale of the number to anyone else who might be reading your code.
Okay, Section 3. This is where things get really interesting. Mutable versus immutable types. It's basically the plot twist of data storage. So about half of Python's data types are what we call immutable. Think of these as values that are entirely locked in stone. Once an immutable variable is created and assigned a spot in your computer's memory, the actual data at that specific location cannot be modified, period. If you try to change an integer, a float, a string, or a tuple, Python doesn't actually alter the existing object. Instead, it does something entirely different. It creates a brand new object in memory with the new value and then just points your variable to that new location while discarding the old one. It's a really subtle but absolutely crucial mechanic to understand for memory management.
Contrast that with mutable types. These are your flexible, on-the-fly data structures. With mutable values, you can add, delete, insert, and rearrange items directly within the exact same memory space after the variable has been created. Lists, dictionaries, and sets are all mutable. When you append a new user to a list or add an item to a digital shopping cart, you aren't creating a whole new list in memory. You're dynamically updating the existing one. This makes mutable objects incredibly efficient for managing live data that's constantly changing as your application runs.
Which brings us perfectly to Section 4, Python Data Collections Explained. Let's organize the chaos, shall we?
Let's organize the 4 main non-numeric collections side by side so you always know exactly which tool to reach for. First up, we have lists, which are defined by square brackets. They're mutable and hold a simple sequence of items. Next are tuples, which look really similar but use parentheses. The core difference here? Tuples are immutable, locked in stone. If you've got geographic coordinates that should literally never change, use a tuple. Then we have sets, defined by curly brackets. Sets are mutable, but they are unique because they do not allow any duplicate objects. This makes them absolutely perfect for mathematical operations or instantly filtering out repeated data. Finally, dictionaries also use curly brackets, but they store data in distinct key-value pairs separated by colons. If you need to quickly look up a user's email based on their username, a dictionary is going to be your best friend.
Before we leave fundamental types, here's a fascinating magic trick straight from the documentation. We all know booleans represent true or false, but in Python, you can actually cast absolutely any value as a boolean. Python just looks at the data and interprets it logically. Any non-zero number, or any collection that actually contains data will evaluate to true. Conversely, the exact number 0 or a completely empty string, list, or dictionary will instantly evaluate to false. This is a fantastic, highly elegant shortcut for writing clean conditional statements without having to write out all that long, clunky comparison logic.
All right, home stretch, Section 5, Checking Types in Python. How do we actually identify our data?
So, we know what types exist, but how do we programmatically ask Python to identify the data our code is currently holding? Well, Python gives us 2 primary tools, the type function and the isInstance function. According to the Vultr developer documentation, understanding the fundamental difference between these two is absolutely critical. The type function is really rigid. It tells you the exact specific type of an object, but it completely fails to recognize subclasses. It doesn't understand that a custom child class might be related to a parent class. IsInstance, on the other hand, is much more flexible. It actively acknowledges class inheritance. If an object is an instance of a subclass, isInstance correctly recognizes it as belonging to the parent class too. This makes isInstance the absolute go-to choice for object-oriented programming.
To sum it up perfectly, the Vultr docs say, use type function when you need to assert exact type equality without regard for inheritance. Opt for isInstance function when dealing with object-oriented designs. Getting this right is literally the difference between a brittle script that breaks unexpectedly when given a custom data type and a robust, scalable application that handles complex inheritance elegantly.
We've covered an incredible amount of ground today, from the strict naming conventions of variables all the way down to the nuance of checking object inheritance in memory. Now that you truly understand how Python handles the deep identity and the mutability of its data types, I want to leave you with this. How will you use isInstance to build more flexible, dynamic, object-oriented programs in your next major project? Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you in the next one.